What I want to do today is more examples of Turing machines. As you saw last time, they can be a little bit complicated, and we're going to do some more, yet more complicated ones today. I thought I'd start off with one that's not so complicated. So just more Turing machines. How about a Turing machine for what we call the Dyke language? This is the language of balanced brackets. So that would be strings that look like, bracket, bracket. This kind of thing. So that is accepted in this language because if you look carefully, you will be able to verify that the brackets are properly balanced in that particular string of brackets. So the whole alphabet is just the left bracket and the right bracket, and the string is accepted if they are appropriately balanced. This, if you recall, I don't know if you remember, but we made a stack machine for this language, and a stack machine is actually very simple for this language. You just, every time you see a left bracket, you add something to the stack, and every time you see a right bracket, you remove something from the stack, and that's all it takes, really. This language is perfectly suited for a stack, although it's harder to do on a Turing machine. You might think, can't you just use the tape of the Turing machine like a stack? And the answer is kind of, but not really, because remember the way the Turing machine starts is all of this stuff will be written on the tape to begin with. So it's not like you can use it like a stack in the sense that you start with nothing there, and then as you read one letter at a time, you grow the stack, or maybe you shrink the stack. You can't really do that when your string looks like this. But actually, it's not so hard to do this. So we are also going to do this with sort of a marking type strategy, which is how we did the A to the N, B to the N language last time. Although even that takes a little bit of thought. Once you have the correct idea, it's not so hard to write the machine to do it. But for example, if I'm marking, the first thing that I encounter, of course, is this one here, right? And if I were to somehow mark that one off and then make the machine proceed from there, which, and I suppose the idea would be to mark off the one that matches with that one. And then you keep on doing that until everything has been marked off. Which one matches that one? If you have to kind of look carefully to tell. It's this one over here that matches that one. Now, as your machine is going, sort of moving, the head, starts here, and then the head moves to the right. How do you know which of, it could be that one, or that one, or that one, or that one. It's actually that one, though. And how do you know which of those? The answer is, it's complicated, right? If you're trying to describe, in terms of a Turing machine where the head only sees one letter at a time, one of these characters at a time, it's not, to me, not obvious at all how you would even do that. But if you have the correct sort of tricky trick idea, this is not an obvious idea, but it turns out everything is very simple if, instead of matching a left one and then going to find the right one that matches, if you start with a right one and then go to find the left one that matches, that is always easy. See if you agree. I'm going to erase this stuff. Instead of starting with the first left one, we are going to find the first right one, which would be there. And where is the left one which matches that right one? It is immediately to the left. It's right there, right? The matching one, every time you see a right guy, the matching one, so these two match, right? This one here matches that one, which is immediately to the left. The next right bracket is that one, which matches there. The next right bracket is that one. Now, this one doesn't match what is on its immediate left, but it does match the first one that you get to if you're going to the left, having already matched up the previous ones. All right, so our strategy here is you mark the first right bracket, and then you move to the left to find the first left bracket, which has not already been marked off. So you mark the first right bracket and then move left and mark the first will say unmarked left bracket. All right. For some strange reason, this kind of works very nicely when you mark the end bracket first, and it works terribly if you try to mark the left bracket first. This is a strange but true fact about this language. All right, you mark the first right bracket, and then you move to the left, and you mark the first unmarked left bracket that you encounter, and that gets it done. All right. Now, in this example, actually, when I mark things in the previous examples, I had like A's and B's, and I changed them to A bars and B bars. You could change these to like left bracket bar and right bracket bar. Actually, it's not really necessary to sort of remember which one was a left and which one was a right. So I'm going to mark everything. It turns out to be easier. Mark them all as, I'll just like change it into a X. So a X means it's a bracket. I don't really care if it used to be a left bracket or a right bracket. It's just a bracket which I have already dealt with. All right. You can mark them individually with bars or whatever, but it turns out that just makes the machine slightly more complicated. All right. So for example, if I had on my tape, like if my original string was this, what I'm going to do is sort of in steps. This would first become that. I find the first right bracket and mark it by making it an X. And then I would move to the left looking for a left bracket, and that would mark this one right there. All right. And then I would, my head after this, my head is sort of over here. I, again, look to the right, searching for the first ending bracket that I find, which is this one here. And the next step, I would mark that one. So it'd be XX. Left, X here. And then back to the left one spot to match with this one. All right, I'll just say, etc. That's the plan here. All right. If I were to write in words what I'm doing, I would say we move to the right past any left bracket to search for the first right bracket, right? And then mark a right bracket. And then move to the left past any previously marked things, and then mark a left bracket. Like that. This is my strategy in words. Let's see if we can make this into a Turing machine diagram. So I'm going to begin in my starting state. Move to the right past any left bracket. Anybody want to suggest how do I make that happen? Anyone remember these examples from last time? Anyone sufficiently awake at this hour in this economy? Yeah.
BC left and then like read left, change to left and go right.
Yes. Yeah. So it's like this, right? A looped edge. Left bracket, moving to the right. Yeah, that will move to the right past any left brackets. A little technicality, I think in later steps, we should also at this point be moving perhaps through some previously marked brackets also. You might have to go through some things that you've already handled in previous steps. That would look like XXR. That is, move to the right through any already marked brackets. All right, and then it says mark a right-hand bracket. So that you want to do over and over again because you may have to move to the right several times. This really just happens once, and so that needs to go to another state. And to mark a right-hand bracket means I read the right-hand bracket, change it to an X. And you have to move some direction. I think probably we should put an L here because in the next step, what we're going to do next is to repeatedly move to the left. So you might as well start off moving to the left at this point. All right, so there's going to be another state here. So once you make it over to that second state, I have seen one right bracket, and now I'm moving to the left, searching for a left bracket. And so I said move to the left past any X's. That looks like this, XXL. Not my t-shirt size. And then eventually I arrive at a left-hand bracket. I should mark that off. And basically, I think at that point, I have sort of done one whole kind of loop through this thing, and I want to just like do that again. So this actually is going to work out if I just go back to the first state like this. Mark a left bracket, so that is left bracket x. And then I suppose I'll say r here. I'm not sure it really matters what direction you move after that point. All right, so this is basically the whole thing. This will find a right bracket and then move to the left until it finds a left bracket, and then change that left bracket to a r. And then it'll, keep on doing this business. It has to move to the right every time to find the right bracket, and then it goes back to the left to find the left bracket. This is basically it. Anybody have questions or objections? This is not entirely, there's some business that we still have to do here. What's remaining to do, to think about? Yeah?
Accepting state.
Yeah, when is the string going to be accepted at the end? And you have to think this through. Anybody have an idea? At what point will you sort of realize that you're done and the string should be accepted? Yeah?
If you have all x's.
Yeah, if the string ends up being all x's, is there a way to tell when that's going to happen? This is actually not quite so easy in this case. You might think that you might notice that here. If you find yourself in the original state, let's just think about after you mark the last x. Now the last x might be this one. Like in this particular example, the last x is going to be this one. But I think that's not always going to be the case. For instance, if this string had another block like that, then I think this guy would be the last one. But anyway, after marking the last one, you will find yourself back in the starting state. And from the starting state, it's going to do this loop again. And eventually, if you're really all done, everything will be x's, and it will go all the way to the end, and you'll see a blank. I think this is your signal that you're done. That if in this state you see a blank, that's because you did this loop here, and you ended up all the way at the end seeing only x's, or I suppose only left brackets, but I don't want to think about that at the moment. If you see a blank here, then this is your signal that you are basically done, although there might have been left brackets left over in the string that you need to worry about. And so we're going to do one last sort of cleanup step. This often is necessary in the Turing machine. We're going to go back through the string to the left, because we're like on the right end of the string at this point. We have to run back through the whole thing to the left and make sure that it was all x's and no extra left brackets. So I'm going to say BBL here because I intend to run through the entire string again from right to left and check that it's all x's. The way to do that is like this, XXL. So I'm going through every character. If it's a x every time, then this will actually make it all the way to the front. And I'll say something like BBR or whatever, and then accept. So what this little thing does is, when you're at the blank at the end, you go back through the whole thing. If it's all x's, you'll eventually see a blank at the other end, and then that means the string should be accepted. All right. I think that does it. Any thoughts about that one? It's a little tricky. I mean, the machine itself is fairly simple as far as Turing machines go, but I would say the idea, the strategy here is not exactly obvious. All right, great. Let's try. I got another one. I have more sort of increasing complexity for us today. This, of course, is an example of a non-context-free language. So Turing machines definitely can do languages which are not sorry, not, this one is context free. It's not regular, that's what I meant. But the next one I want to do is not even context free. Anybody remember, there's one example of a non-context free language that we've talked about? Anyone happen to remember? Yeah?
Is it A to the N, B to the N, C to the N?
Yeah, it's A to the N, B to the N, C to the N. This is not context free, but you can make a Turing machine for this language. A to the N, B to the N, C to the N. And actually, the Turing machine for this is not much more interesting or complicated than the one for A to the N, B to the N. If you recall, the strategy for A to the N, B to the N was by marking. You mark a A, and then you go to the right and mark a B, and then you go back to the left and mark the next A. Can you just do that for this one? And the answer is, yeah, basically you can. You mark an A, and then you go to the right and mark a B, and then you continue to the right and mark a C, and then you go all the way back to the beginning and mark the next A. So this really is more or less a fairly simple modification of the examples that we did last time. So this one, the strategy will be mark a. I'm going to write it as a A bar. In this one, you really do need to remember sort of which ones used to be A's versus B's versus C's. And then I'm going to then move to the right and mark a B. Then move to the right and mark a C. And then you go all the way back to the left until you find the next A to mark off. I will say move to the left and repeat. All right, it's a fairly straightforward modification of the one that we did last time. Let's see if we can write out the details for this one. So when we begin, the head should be pointed at the first A, which I'm going to mark off. That is to say, turn it into a bar. So this is like A bar. And I guess I'll say R there because I want to now begin moving to the right to search for the next B. All right. In this state, I am going to move to the right over and over again. That looks like a looped edge like this. And then, can somebody say what should be written on here? You have to think, as I'm moving to the right, I'm going to go through a bunch of letters without modifying them. What do you think? Yeah?
A-A-R.
Yeah, A-A-R. So you will have to, as you are going to the right, you will have to move through some other A's that are not yet marked, right? You know, a typical string in this language is something like A, 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 B, 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 C, C, C. So if you imagine, I just marked off the first A. I'm now moving to the right. I have to go through some A's. In later steps, you may, in order to find an unmarked B, you know, a typical intermediate step would look like that, where the first A might be marked off, the first B and the first C might be marked off. And so when you, after marking an A, and when you're searching for the next B to mark, you might have to go through some previously marked B's. You should not see any C's though, so I'm not going to put any C's here, but there could be a B bar, R. So you may have to go through some B's that you marked in previous steps. All right, eventually, after you go through the A's and the B bars, you will arrive at a B, which you should change to a B bar. And so that's going to go out to another state, B bar. I'm going to put another R because after that, I'm going to continue moving to the right and look for a C to mark off. So in this state, from here, we move to the right over and over again. Somebody else want to tell me what should I put as labels on that one? You are thinking about, like after you marked off this guy, I want to move and find the next C. What do I have to go through? Yeah?
B and C bars?
Yeah, B's and C bars. So I want to move to the right through any B's. This says BBR. And through any C bars. That's C bar, R. You don't want to change those guys, wherever they are. Okay. And then you will arrive at a C, which you mark, and then start to move to the left. Now, that is basically the end of one full sort of repetition through this process, but you shouldn't, sometimes it can be a little tricky to ask, you know, should I go back to the original state here? Actually, you need another state which is going to move you back to the left over and over again, which is not the starting state. So there's going to be one other state here. This will say C, C bar, L now because I'm going back to the left. And then this state on the bottom will have a loop on it, which says move left over and over again until you get back somewhere, I suppose. We'll have to think about where exactly do you want to get back to. Actually, could we answer that first? I'm going to move to the left all the way back until what? Yeah?
A bar?
Yeah, until you see A bar. That's the sign that actually you overshot the beginning by 1. Because really what you're looking for is this guy here. But you can't tell that, you don't want to stop at the first A you see. So the way to make this work is you stop at the first A bar you see, and then you move to the right by 1 position. So this is going to say A bar, R. And that's really one full rotation. Now what about the looped edge on the bottom? This will describe, you have to put labels on here for all the different kinds of letters that you want to go through as you're moving to the left. And actually there's a lot of them. So you have to imagine I just marked this C, turned it into a C bar. As I'm moving to the left, I'm going to go through some C bars, also go through some Bs, also go through some B bars, and also go through some As. So there's going to be many labels on this arrow. What did I say? C bars, Bs, B bars, and As. Right, those are all the different letters that you might have to push through as you're moving to the left. All right, this is basically it. Now you need to say something about how you decide when to stop. I think the answer is if you do this. Well, yeah. How do you know when you're done doing this big loop over and over again? You have to think about what will it look like after everything is marked. And you go through this, you see an A bar, you move 1 step to the right. What will you be looking at if everything has been marked off? Yeah?
Would be another A bar.
Another A bar.
B bar.
I think it's a B bar. Yeah, if you think about how this procedure works, let's imagine you're actually done. Everything is marked off. What you just did, like the last mark will be this one. This C has been marked off. And then you do this, move to the left over and over again until you see A bar. That's here. Then the last step here says A bar, R. So after you do this, you will be right there. You'll be looking at a B bar. So the trigger for the end here is if in this state you see B bar. That basically means all the A's have been dealt with. Now it doesn't necessarily mean, so I'm going to do another one of our little sort of end game, B bar, R. And now we must run through the rest of the string and just make sure there's no extra funny business left over. So what I should see left over in the string is a bunch of B bars followed by a bunch of C bars. And actually they are not allowed to be mixed up together, not like B bar, then C bar, then another B bar. So really what I'm going to do is I go through here, I want to see all B bars, and then I'm going to see all C bars. That's like this, C bar, R, all C bars, and then finally I'll get to the end, which is a blank. All right, so this sort of trail at the end here is to verify that what remains on the tape is a whole block of B bars first, followed by a whole block of C bars, followed by nothing else. That's how we do it. All right. So I will just refresh our memory. This is a little diagram that I like to write all the time. These are the regular languages, are A to the N. There's the context-free languages, which include A to the N, B to the N. And then there's A to the N, B to the N, C to the N, which is not context-free, but you can do it with a Turing machine. This one would be like the NFA languages. These ones are like the stack machine languages. These are like the Turing machine languages. All right. A to the n, B to the n, C to the n, you can do using a Turing machine. Anybody want to get crazy with this? What about A to the n, B to the n, C to the n, D to the n? Is that even crazier? Or do you think you could still do that using a Turing machine? I see some nods. I think, yeah, I mean, basically, we're not going to do it, but basically this will still work, even for A to the n, B to the n, C to the n, D to the n. Actually, there is, for mysterious reasons, there's like a big difference between this language and this language, but adding more things, A to the n, B to the n, C to the n, D to the n, is not really very different from that from this point of view. So Turing machines can do this. I will just say, this is easy to adapt to get A to the n, B to the n, C to the n, D to the n. All right, that's not really a problem. What you would do is basically this 4-step loop here, you would add an extra step which continues to the right and then marks off a D. And then you would have to add one other step here also to make sure that you see, after everything's marked, you want to see only B's followed by C's followed by D's. But that would be fairly simple to do. All right. Yes?
So for when you're leaving the main loop in that, why can't you group the B bars?
This guy?
Yeah. And then you go to, why can't you group the B bars and C bars together in that?
Yeah, this is a good idea. This would, and it may be that is still proper. What I'm trying to do here is we check for, we have the A bars, which we don't really have to check for them because they have already been accounted for up here. But then really what we're checking is that the rest of the string is all B bars followed by C bars. Like this is the part that we're checking at the end there. The reason I split it up into first the B's, then the C's is to distinguish this versus something like B bar, C bar, B bar, like that. This should be not allowed. Now it may be that if your string actually looks like that, then you would have got stuck already up here. That's probably true, but I'm just trying to be explicit about it. What I need to check is that it's this format. So you check the B's first, followed by the C's. Great, good question. All right, can we do another one of slightly increasing complexity? Oh, I was just going to say, it is around this time that you should start to wonder, is there anything outside of this region? The standard way that we make a harder language is by just sort of adding more stuff, right? If you just continue this pattern, actually you don't get anything harder than that. So is there any language that you can't do on a Turing machine? This is a big question. The answer is, do you want to spoil the answer? The answer is yes, there are languages that you can't do on a Turing machine, but they are truly insane. Like they're not anything that you would ever think of on your own. We are going to talk about them after the break, and they are very very interesting in my opinion. But there are things outside of this category. They're just so crazy that you would never. I hope it's not insulting to your intelligence. You would never think of them on your own. Actually, the one out here is this. It has a special notation for it. That's how weird it is. You can't write it in terms of like A to the N, whatever. It's just a very, very strange example language, which was specifically constructed in order to be outside of this category. But anyway, we'll get to that eventually. I want to do, I'm just trying to do more practice actually creating Turing machines. How about, this is a fancier one. This is actually quite a bit fancier. A to the N, B to the M, C to the N plus M. So, what we have here is some number of A's, followed by some other number of B's, and then a number of C's, which is equal to the amount of A's that we had plus the amount of B's that we had, right? The number of C's, the total number of C's is the same as the total number of A's and B's, all right? So you can do this by matching also. My strategy is going to be you mark a A and then you go mark a C. And then you continue marking all the A's matching with C's. And then when you're done with that, you also mark each B matching with the C. And then when you're done with that, everything will be marked off and you'll be done. So that's the strategy. Now it sounds simple when I say it that way, but actually if you think through how to make this work as a Turing machine, it's a little complicated. So my strategy though is to mark A's and matching C's. And then mark B's and matching C's. So for instance, if my string was something like this, AAB, CCC. In this case, N is 2 and M is 1. And so C should be 3 C's. The strategy would be mark this A first, then mark this first C to match it, then mark the next A, and mark the next C, and then mark the B like so, and mark the last C with it. All right, mark the A and any matching C's, and then mark B's and any matching C's. What's a little complicated about this is actually each of those two things is its own loop. Like each of these things is something like the language for A to the N, B to the N. So the structure of this has a loop here, followed by another loop here. So the large scale sort of shape of this thing, the shape of it is something like I start here and I do a loop like this. This is where we mark A's and C's. And then when you're done with that, it runs into another loop like this, where you mark the B's and C's. And then there's some thing at the end here, as we usually have, to make sure that everything is looking how we like it at the end. All right, so this is the basic shape of this loop here. So I'm going to try to draw two loops, and each of those two loops will look more or less like the A to the N, B to the N language, or the machine for A to the N, B to the N. All right, let's see if we can do it. So we got, my first loop will be mark the A's with the C's. This one, just because I have done this before, I know this is going to have 3 states, just like the A to the N, B to the N language had 3 states. So in the first state, I begin by marking A. That's A bar R. And then we have to move past other things. Remember, a typical string in this language looks like this, maybe. Right? 2 A's, 3 B's makes 5 C's. And after the first couple steps, it may look like that, right? Maybe I've marked an A already and a C already. After marking the first A, you need to move to the right to find the first C. As you're moving to the right, you will go past other unmarked A's, so I'm going to put AAR. I'm imagining, what do I have to go past in order to make it to this C? I also will go past some unmarked B's. That's a BBR. And I also might go through some C bars. But that's it, not C's. When you see an actual C, you should mark it. So I go C, C bar, L, because now I'm moving back to the left. And now I want to move to the left over and over again, basically all the way back until you see an A bar. So this is going to say C bar L, BBL, AAL, and then when I see A bar, I go A bar R, and then I'm back at the beginning state. All right, so that's my first loop, marking off A's and matching them with C's, like so. All right, and how do we know when we're done with this? When you're done with this procedure, where you'll end up is all the A's will be marked off and some of the C's will be marked off. And after this step here, you will have moved to the right just after the last of the A bars. It will look something like this. And you will have just marked this guy. You go back left, 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 left. You see A bar and you move to the right and you see B. So when you are in the starting state and you see a B, that means it's time to transition to the next loop. The next loop will be marking these B's with these C's. So if you're in the starting state and you see a B, that's when you transition into the next loop. Now I'm going to just draw the next loop like this, and maybe I will draw the transition arrow from the first to the second loop in a moment, because it's not quite obvious. But anyway, this loop looks just like this one, only instead of A's and C's, it's B's and C's. And when you're moving various directions, you actually will never see any A's or A bars ever again, because you're past here and you're going back and forth like this, marking these guys. So this one is B bar R. This loop says, I hope I have enough room to squeeze them in, BBR, C bar R. This is C bar L. Everything the same, it's all about B's and C's now. There's no A's involved anymore. This is C bar L, BBL. And you move back to the left until you see a B bar, and that will take you back here. So this is B bar, R. All right, this is my second loop. And this one, so this one marks the A's with the C's. This one marks the B's with the C's. Mac. All right. The question that I was delaying is the arrow that goes from here out. Where does it go to? Like from here, should I go to the starting state here or down here? Now we said sort of the trigger for this is you will know that you have finished your first loop when you see a B at that point. And what should you do? You should mark that B and then move to the right. So this arrow, as it comes out, the label will be B bar R. All right? Because at that point, you're going to mark that first B bar. Can anybody say then, where should it actually go into in the second loop there? Your choices are this guy over here, or this one here, or this one here. You have to jump in at the appropriate time in this loop here, yeah?
So one kind of top state.
Yeah, I think it's the one on top here, because, I mean, I'm doing the same step that this arrow did, and so actually when you do this step, you should really go into this state rather than what you might have thought was the first state, so like that. All right. All right, finally, what about the acceptance? So the acceptance, like before, happens here. This is how you know that you're done. When you are in this position, and that would be you marked your last C bar, you go back to a B bar, and then you move once to the right. I believe if you see a C bar in this position, that means that you're done. So I say C bar R, and then as usual, we have to check that all that's left over are C bars until we get to the end, and then finally accept. That's how we do it. It's a little complicated. 2 separate loops. All right. And I hope you don't mind, there is one more very slight complication, and that is, what if there are no B's at all? That is allowed in this language, A to the N, B to the M. What if there aren't any B's at all? One thing you might have wondered, what if there aren't any A's at all? Isn't that also a problem? Actually, that would be fine. If there aren't any A's at all, the string starts with a B, and you immediately go into the second loop, so everything's good. But if there are no B's at all, that means you start with A's. You could still go through this thing. It's just at this step, you wouldn't end up at a B, you'd end up at a C bar. This would be if there are no B's at all in the string. What do you do then? That means actually you're completely done at this point. Really, you should go directly into this little end game here. So there's one more arrow like this. That's another C bar R. So that arrow is for strings, sorry, I can't see it. That arrow is for strings which don't have any B's at all. You have to skip over the middle loop in that case. and go straight to the end. All right, this one I would say is complicated to get it totally right. I hope that I got it totally right. All right. We got 10 minutes. I got one more. Would you mind one more? I know these are tricky. I have some examples for you guys to try also, but I guess they'll have to wait till next time. I had one more. So this is one sort of way that they can be more complicated. That is to say, you might have two separate loops that you have to patch together. One more, and that is a Turing machine for the language where the number of A's equals the number of B's. This is different from A to then B to then because the letters might be like mixed up in any possible order, all right? It's not so, again, this one has sort of a simple idea to it, although it can be a little tricky in practice to work this out. So that's an example of a string in this language, or something like this is another example of a string in this language. What we're going to do is, the strategy is mark the first letter, and then move to the right and search for sort of its complementary pair. So if you marked an A first, you match it off with a B, and if you marked a B first, you match it off with an A. And then you continue like that. So I'm going to say mark the first letter, then find a matching other letter. That is to say, if you mark the A first, you need to match it off with a B. And if you mark the B first, you need to match it off with a A. And then I'll just say, repeat this until you've marked everything off. Right? If you mark everything off in this way, that means there must have been the same number of A's and B's. And if there's like extra A's left over, that means there were too many A's and it should be rejected. Mark the first letter, then find a matching other letter and repeat. All right? What's tricky about this one is you have to sort of remember what was the first letter you marked. Like, if I begin by marking an A, then I move myself to the right looking for a B. But if I begin by marking a B, then I move myself to the right looking for an A. These are two different behaviors depending on whether you saw A first versus whether you saw B first. So this is a simple idea, but if you think about it in detail, really what we have is different behaviors if we saw A first versus B first, right? And how do you handle that? This can be easily handled by sort of two branching paths. So we're going to make two branching paths, and basically the two paths will do the same thing, but with superficial modifications. It's still sort of like one big loop, but that big loop will have two different pathways depending if you started by seeing an A versus starting by seeing a B. So I am going to try and make this happen like this, all right? Two branching pathways. Let's say we take the top route if we begin by seeing an A. So if we begin by seeing an A, I'm gonna mark it off and move to the right. And then continue moving to the right, looking for a B. So this means I have to move through, you might have to move past other A's, which I am not interested in. I might have to move past other marked A's, that's possible. A bar, R. And I also might have to, sorry, I didn't leave enough space here. I might also have to move past other marked B's. All right? But I'm looking for an unmarked B. And when I see an unmarked B, I mark it, and then I start going back to the left. So when I see an unmarked B, I go B, B bar, L. All right? So this whole thing here, if I were to describe in words, this mark A first, then move to the right through a bunch of other stuff, and mark a B, right? And then What about the other way around, the other branching path here? So this one is going to come back to the same point, because once you match it up, then it doesn't matter anymore which one was which. So it's really just one step of divergence in the two paths. The other path is, what if you started with a B? Then it should say B, B bar, and then you move to the right over and over again, looking for an A to match it up with. So I got to go through B's. I might have to go through A bars, and I might have to go through B bars. So that state at the bottom there is moving to the right, eventually looking for an A, and then you should mark that A. So over here it'll say A bar, L. So after doing that, we have marked one letter and matched it off with one other letter, either way around, and we end up in the same place. Now this really should be a loop, so there needs to be an edge from here going back to here, and I have arranged this so that I could insert one edge in a cute way, just going straight back like that. So this makes a loop with a branching path. What happens in this state? In this state, we need to just move all the way to the left, looking for, this is a little counterintuitive maybe, but really what we want to find is the first unmarked letter, but there's no way to tell which, as we're moving to the left, which is the leftmost unmarked letter. Really, you have to go all the way back to the beginning of the string until you see a blank. So this is going to go a loop left through absolutely everything. So this is A-A-L, B-B-L, A-bar, A-bar, L, B-bar, B-bar, L, all the way through the entire string until you see a blank on the left end. So this will be a B, B, blank, blank, R. All right. And there's one little sort of technicality, is that in this state, after you do that, you go all the way back to the end. It's likely that the very first character in the string has already been marked from a previous step. In fact, it definitely will be already marked. You have to, in this state, push your way past all of the already marked ones. So I'm going to do that like this. A bar, R, B bar, B bar, R. So that means that even in the starting state, you will automatically move to the right through any ones that have already been marked before you try to do this whole loop. In our remaining 2 minutes, can you say how do we know when we're done here? What will happen? As you've seen in previous examples, usually you realize you're done in the starting state in one of these loops. That's perhaps not a surprise. I mean, when you're doing something which is a loop, you don't finish typically in the middle of the loop. You finish after one of the loops has ended, which will put you back at the beginning. How do you recognize from this state when the entire thing is done? Yeah?
It'll be blank?
It'll be blank, yeah. It's because this thing will have happened. When you're done, everything is marked off. And when you're back in the starting state, this will run all the way to the end of the string. And so blank, blank, R. I think actually you already know that everything is done at that point. There's no extra checking to do because it's all definitely finished. All right, so this is the old branching paths strategy. A little tricky. We'll do a few more examples and I'll give you some time to try some on your own next time also. All right, and we will have homework due next week on this business. Hope you all have a good little break. See you next time. Thanks.